All right, let's do another example where we predict the molecular geometry of a species using valence shell electron pair repulsion theory. So in this example, I would like us to draw the best possible Lewis structure for I3 minus, also known as the triiodide ion. And I would like us to figure out what the bond angle is between those three iodines. So they're all bonded right in a row like that. So if we want to try to figure out what the best possible Lewis structure is for this one, I have three iodines, and each of them brings 7 electrons to the table. I also have a negative charge on that ion, so I can count that as 1 electron. So I can count the negative charge as 1 electron. So that's 21 plus 1, or 22 electrons that I have available. Now, three iodines to obey the octet rule would be 3 times 8, so 24 electrons are required, minus the 22 electrons available tells me that 2 electrons should be shared. And if I divide that by 2, that would give me only 1 bond. Now, can I create the triiodide structure, I, with only 1 bond? No way. That cannot be. That is impossible. So the handy hints are sending me down the wrong road here. This must be a case of valency expansion because the octet rule cannot possibly apply here because that just will not work out to build the molecule with only 1 bond. So since I'm throwing the handy hints out the window, I am just going to try to build that iodine, triiodide ion, the best I can by using the electrons that I have available. So I have 24 electrons available, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 22 electrons available, as I calculated before. And I need to figure out how to arrange them. So one thing that you may recall from the previous chapter is that the only atom in one of these small molecules that can expand its octet is the central atom. We'll talk about why that is. It's because you have the d orbitals that are involved in the octet expansion. So these terminal iodines still have to obey the octet rule. So I just filled up their octets. So now I've spent 2, 4, 6, 8, 10, 12, 14, 16 electrons. And I need to have 22 electrons total kind of arrayed in my compound. So what does that mean? 22 minus 16 means that I'm going to have, oops, I don't know what's going on with my response time here. So just give me a moment. 22 minus 2, 4, 6, 8, 10, 12, 14, 16. 22 minus 16 gives me 6 electrons that remain. And the only place that I can put them on is on that central iodine. The central iodine has to be the one that expands its valence. It's the only one that can. And if you go around and figure out what the formal charges are on the atoms, this central iodine is going to have a -1 formal charge, whereas the terminal iodines don't have any formal charge. So that formal charge is what gives the negative charge on the triiodide ion. Okay, so that was the Lewis structure of triiodide. Now let's figure out what the substituent number is on that iodine. So if I go around, I have 1, 2 bonds, and then 3, 4, 5 from the lone pair. So the substituent number around that iodine is 5. So we have a substituent number of 5, and we have 3 lone pairs around that central iodine. In order to figure out what the geometry is, I have to go up to my Vesper theory handout and look for a situation where I have a substituent number equal to 5 and 3 lone pairs on the central atom. And in that kind of situation, okay, I'm just going to tell you because I can't see that handout at the moment. In that situation, I am going to have a linear geometry. That's because if I have a substituent number of 5 and it's all bonding pairs, then I have a trigonal bipyramid. But here, instead of having bonds around the equator of that trigonal bipyramid, I have those lone pairs around the equator. So the bond angle here is going to be 180 degrees. Basically, those iodines are going to be as far apart as they can from each other. So this is going to be a linear geometry with a bond angle of 180 degrees.